So hello everyone. So in this lecture we are going to see the relationship between speed up and efficiency. So previously we had seen what is speed up, what is efficiency, all these things we had seen, right? This is one of the performance metrics, right? Now we will see the relation between them, right? So the relation between speed up and efficiency is that number of stages into efficiency is equivalent to speed up. Are you getting it? Now, what does it mean is, see, suppose we have m stages. We already know, right? We have m stages, which is 4, right? And suppose efficiency of our pipelining is 75%. Okay, these all are given. Then if I want to calculate speed up, what would be the speed up? That is S, right? Then what would be the situation? Let's see, right? So how I got 4 stages? We already seen all this thing, right? 4 stages because of this, right? This FaceTime diagram we have we know all this thing, right? We already seen it, right? Because of this I am taking it as 4 and efficiency I'm considering as 75%, right? Now let's see what would be the speed up. Now if you want to calculate speed up, then what would be the thing? M into efficiency equal to speed up. What is M here? 4, and efficiency is 75%, right? Equal to S. Now you tell me, you see, if it is already given 75%, right? %. So 75% is equivalent to 3 upon 4, right? Can I write like this? Yeah, definitely. So what I will do is I will write 4 into 3 upon 4. Okay, now I can cut this 3, this 4 and 4. Then what is S? S is equal to 3. Right? So what is the meaning of this? That is what you have to understand. Right? We got speed up equal to 3. So we also seen back then also we got speed up equal to 3. Right? Where we got here, right? Here we got speed up is equal to 3. Right? The same thing we are getting here. So what is the meaning when we are taking a relation between efficiency and speed up? Okay, so the meaning is, we can see here, that if a pipelining technique, this means that a pipelining technique is 3 times faster, then our pipelining technique is 75% more efficient. That is the meaning of it. That means if our pipelining technique is 3 times faster, then our pipelining technique become 75% more efficient. Or in vice versa, if it is 75% more efficient, then it is 3 times faster. Okay, so that is the relationship between this speed up and efficiency. Fine. Now let's see if our pipelining technique is 100% more efficient, then what will happen? Okay, then this is our formula, right? Then let me make it 100% efficient. That means M is 4, right? Means number of stages 4, and efficiency is 100%. Then what would be the speed up? See, 100% means it is equivalent to 1, we can write, right? So speed up will be what? 4 into 1, which is equivalent to 4, right? And 4 is how many number of stages we have? That is also, and this is equivalent to M, right? So we can clearly see M into efficiency is equal to S, right? So if I make this as 1, then what will become? S equal to M, right? So speed up is equivalent to M. What is M? Number of stages. Here we also got same thing, S equal to 4, and 4 is equivalent to how many number of stages we have? 4. So what is the relation we got is S is equivalent to M. What is the meaning of it? So what is the meaning is that whenever we have 4-stage pipelining, then our speed up should be 4 times faster. Then only you will get 100% efficient pipelining technique. Okay, that is the meaning of it. Whenever we have 4-stage pipelining, then your speed up should be 4 times faster. Okay, then only you will get 100 times more efficient pipelining technique, which is near to impossible to achieve. Okay, why it is near to impossible, I am just coming to that point. Okay, I will explain it with one derivation with mathematics and some few theory concept, right? So achieving this speed equivalent to m, if it is possible, then this is called ideal pipelining technique. It's a perfect pipelining technique. Are you getting it? Which is very much means there is no delay in your pipelining. Are you getting it? So this is near to impossible practically. Theoretically it is possible, but practically this kind of efficiency 100% is definitely not possible practically. Okay, so whenever, if 100% is not possible, so speed of can never be equivalent to m. You have to remember this point. Okay, right. So I had written here also, when m is equivalent to s means pipeline is 100% efficient and giving a maximal theoretical speed up. Okay, which is theoretical speed up I am talking. Practically it is not possible. Fine, theoretically it is possible, right? This is one point you have to remember, very important. Fine. Okay, now I want to prove why s equal to m is not practical possible with some mathematics. Okay, I want to prove it with a derivation. So we already knew that s is speed up is equal to time taken without pipelining and time taken with pipelining, right? Now without pipelining, what would be the formula? Number of instruction. Okay, each instruction take m clock cycle, right? And with pipelining, first instruction will take m clock cycle and the remaining n minus 1 instruction will take 1 clock cycle, right? With this we had derived one formula, that is n into m, right? M plus n minus 1, right? Now what I can do is, okay, can I write like this? I just removed the, sorry, I just removed the bracket. Right, now I will, what I will do is n into m, right? I will move this n here because plus is associative, so I can do that. Right, now I will divide okay, and, so I will divide n in numerator and denominator. Then let's see what will happen. So I will do like this, right? M in numerator and denominator also I will divide it with n. Okay, so let's see what will happen. This n will get cancelled, right? And we can write like this, m divided by this, I can write like this, right? N divided by n plus m minus 1 divided by n, right? Now this n got cancelled, and which is equivalent to m divided by 1 plus m minus 1 divided by n. Okay, see, I want to make one point here, that's why I'm solving this part. Fine. Okay, with this we can understand that we got one formula, that is s equal to m 1 plus m minus 1 divided by n, right? Now we can observe that this is n. What is this n? This is number of instruction, right? Now if I want to make s equal to m, then what should I do to achieve this part? I have to make this entire part a 0, right? If I make this entire part as 0, then what will become? This entire part is 0, then 1 plus 0 is 1, then we can achieve s equal to m. Now how can I make this entire factor as 0? How it is possible? For that, what you have to do is, you have to assume n equal to infinity. Okay, what is the meaning of it? The meaning is that you have to give infinite number of instruction to the pipelining. Okay, that is the meaning of it. I will explain. I'm coming to that part. So when you give infinite number of instruction the pipelining, then S become m plus m minus 1 divided by infinity. Okay, and when you are dividing anything with infinity, we already know that that particular factor becomes 0, right? So we got S equal to m. So we can directly get S equal to m. Okay, just making infinite equal to infinity. Understood? So what is the meaning of it? The meaning is whenever we give infinite number of instruction to the pipelining, then we can achieve this speed up equivalent to number of stages. But why I'm giving infinite? See, I told you speed up depend upon the load of instruction. How many number of instruction you're giving, depending upon that we will calculate the speed up. Now here what we are doing is to achieve this S equivalent to m, I am giving infinite number of instruction, which is practically not possible. How can you give an infinite number of instruction to any pipelining? Infinite is not even a number, right? So theoretically I proved it that this particular part is not possible to achieve it. Right, with mathematics also I proved it that S equal to m is not possible. So to get this you have to give an infinite number of instruction, which is practically not possible. So this is one way to prove that S equal to m is practically not possible. Okay, theoretically it is okay, but practically it is not possible. The reason is this only, infinite number of instruction. If you want to achieve an infinite number speed up equal to m, then you have to give infinite number of instruction to the pipelining. Okay, which is practically not possible. Fine, right? So if it is practically not possible, that means if practically S equivalent to m is not possible, then we can derive that with that we can derive that 100% efficiency is also not possible practically. See, also not possible. Okay, so practically 100% must, because this is not possible, then how can a 100% efficiency is possible? Okay, if you have 100% efficiency, definitely this condition should be satisfied, that S equivalent to m, or if S equal to m, then only you can achieve 100% efficiency. Okay, both are vice versa. Now we had already proved that this is not possible because of this condition, which is n equal to infinity. Then how 100% efficiency is possible, right? So with this I had proved that S equal to m is not possible, and that is practically 100% efficiency also not possible. This is a mathematical proof, right? Okay, now I told you that practically this is not possible. Then what is practical possible? So in practice, speed up is smaller than m always. Okay, remember this part. Speed up is smaller than m. This is what practically possible. Okay, now if you observe, if I elaborate this, you can clearly see one thing. What is speed up? Speed up can be written as time taken without pipelining and time taken with it pipelining, right? Which is smaller than m. That is number of stages. M is what? Number of stages, right? Now I can do one thing. Time taken without pipelining is smaller than m into Tp. Can I write like this? Okay, now you can observe one more thing here. Okay, what does it see? Can you see what is the meaning of this particular formula? Okay, so what is the meaning is, see, I have written here, the meaning of it is the time taken to execute one instruction, without pipelining is less compared to pipelining technique. That is the meaning of it. See, I am talking about the one instruction. Be careful, okay? See, it is time taken to execute one instruction without pipelining is always less than time taken to execute one instruction with pipelining. Okay, means with pipelining, time taken will be more compared to without pipelining. See, this is you might be getting confused. See, till now I'm talking about that pipelining technique is very efficient, it will reduce the time, okay, and with compared to non-pipelining technique. And now I'm talking about that pipelining technique is taking more time compared to non-pipeline technique. What it is, right? It is all contradict to what we have learned. No, see here the word is one instruction. This is where you have to be careful. I'm talking about only single instruction. When you are executing single instruction, then there is no concept of parallelism, anything. Whenever I'm executing multiple instruction, then the magic of pipelining will come into picture. Okay, otherwise for single instruction, pipelining technique take more time compared to non-pipeline technique. This is very important, please mark it. Okay, so try to understand. Okay, so for single instruction, this is the thing. Okay, when you try to execute more and more instruction, then pipelining will try to execute in a parallel processing way, right? Then the efficiency will be more. Okay, that's why I told you that whenever the number of instruction is more, then pipelining technique, its efficiency will be more. When there is very less number of instruction, then that parallelism will not work. Okay, and when we are reducing it to one single instruction, you can clearly see what happens. Pipelining technique is taking more time compared to non-pipeline technique. So it is better to use non-pipelining technique compared to pipelining technique when you are executing one instruction. Okay, so this point is very important, right? Want to Now if you want to see why this problem is arising, that when you are executing one single instruction, why non-pipelining technique is faster compared to pipelining technique. Okay, I will explain this part. See what happens is, our CPU, okay, our CPU is completely one single combination circuit. Okay, so when we don't have a pipeline, the CPU is completely one single combinational circuit. This is one single combinational circuit. What is combinational circuit? We have seen in digital logic, right? So whenever we don't have a pipelining, this is completely one combinational circuit. Now whenever you pass, see in this all the particular phases are there. So when you try to, now here you can clearly see each phase. For example, each phase is taking 2 nanoseconds. Here instruction fetch is taking 2 nanosecond, decode 2 nanosecond, execution phase 2 nanosecond, write back taking 2 nanosecond. Now you are trying to execute one instruction, that is I1, right? It will go through all these phases. Okay, it take 2 nanosecond, then it will go to decode phase 2 nanosecond, go to execution phase 2 nanosecond, go to write back phase 2 nanosecond. After that it will come out and it completes execution. How many time it taken? Okay, 2 into 4, how much? 8 nanoseconds to complete its execution without pipelining, right? Now let's see with pipelining what will happen. Okay, now there is one small concept you have to understand why this particular problem is arising. See, when we try to get this pipelining into picture, we try to divide CPU into various functional unit. Okay, we try to divide CPU into various functional unit, and we try to place a buffer and register at every unit. We try to place a buffer and register, this is called buffer, at every unit, right? Why we are doing this, I'm going to explain it next lecture, but this is what happens. Okay, now because of this buffer and register at every unit, at every phase, what will happen? Let's see instruction fetch already taking 1-2 nanoseconds, right? And because of, and this buffer is also will take some time, right? Suppose this buffer and register is taking 1 nanoseconds, right? Now instruction here decode also, like previously taking 2 nanosecond, and this buffer and register is taking 1 nanoseconds. Like now you try to execute one instruction, that is I1. Now what will happen? I1 will try to come here, and this fetch phase, it will take 2 nanosecond, then it will get inside this buffer, again 1 nanosecond, means totally it is taking 3 nanoseconds, right? After that it will come to decode phase, again 2 nanosecond, then again it will go to buffer, completely 3 nanoseconds. Like this it will pass to all this and it will come out. Okay, then we will say that I1 is executed. Then how much time it is taking? Let's calculate. This is 3, right? This is 3, this part is 3, this part is 3, this part is 3, right? 3 plus 3 plus 3 plus 2, how much? So 3 into 3, right, plus 2. So 3 into 3 is 9 plus 2, which is 11 nanoseconds. Can you see that? It is taking 11 nanoseconds. With pipelining, and without pipelining it is taking 8 nanoseconds. Okay, so with pipelining we can see it will take 11 nanosecond to execute one single instruction. I'm telling you, it is all about one single instruction, and without pipelining it is taking 8 nanosecond to execute one single instruction. So which one is better? You can clearly see that if you have a single instruction, it's better you go for without pipelining technique. Okay, because it will be faster. Okay, now in coming lecture I will explain why we are taking this particular register. Okay, why these buffers are all allocated. Okay, we will understand that part, but hope you understood why this particular thing is. Okay, why this speed up is less than phase. Okay, speed up is less than the number of stages. Okay, all this thing we understood, right? Okay, so hope you understood. Because of this reason only, speed up will always be less than m. Okay, and this is what the exact thing is, right? So hope you understood, right?